Greetings. Now we will be talking about Young's double slit experiment and something related to that. We get a pattern in on the screen when we do the Young's double slit experiment, and that pattern is called interference pattern. The pattern looks something like this. Figure 10.13. So this is a band of light and darkness. So there is a bright band, something called a bright band and dark band. And how do we obtain this interference pattern, which you see on the screen, is as follows. So let me just see. Let me just take up a good picture for interference of light, which will tell us how we get. Okay, this one is good. Open image. Yeah. So what we have here is there are two slits, there are two openings, and we send light like this, and it is a monochromatic light. Monochromatic means single frequency. Mono means one, chromatic is related to frequencies. So a single frequency light is exposed on the slits, and you get an interference pattern on the screen. And that interference pattern is exactly what is shown in the textbook here, 10.13. So why does this happen? I mean, a clear example for a clear reason for that is that light behaves like waves. Interference pattern is obtained only when waves are interfering, nothing else. So if we are getting an interference pattern for light, it implies light is a form of a wave. So that is what we have here. And how do we get a wave interference pattern for waves? The answer is something like this. So over here, we have two waves. So these uh, arcs are basically sections of waves, and there are places where the intersection of two waves is in phase, and there are places where the intersection of two waves is out of phase. So what happens when you are in phase and when you are in out of phase, we have discussed. When you are in phase, when two waves meet like this, you get a larger amplitude wave. Okay, and on the other hand, when two waves meet like this out of phase, okay, then you get zero, nothing, no wave at all. So this is like corresponding to bright band, BRIGHT, bright band. What I mean by bright band is this bright patch. Basically, this bright patch is called bright band, and this dark patch is called dark band. So you get a bright band when the waves interfere in phase, and the waves interfere out of phase. You get a dark band. Dark band. Okay, and it so happens that you get a straight line, a locus, basically a locus of in phase interfering waves and a locus of out of phase interfering waves, and corresponding to the former you get a bright band, and to the latter you get a dark band. So can we have a mathematical formulation corresponding to this? Can we have what will be the thickness of the bright band, and what else can we ask? At a certain distance x, Will I get a dark band or a bright band? X from where? From, let me take this copy image. So yeah, from where am I talking about X? From here, let us say this is 0. This is 0. And if in the up direction you have positive X, in the down direction you have negative X. So if this is the X axis, for example, okay. So at a certain place over here, at a certain distance X, from the center, this, why I have selected this as 0, because this line is at the middle of the two slits, so it is a good reference point. So at a distance X from the reference point, will I get a dark band or a bright band, and what will be the thickness of this bright patch, etc. We can have a mathematical formulation for that, and that mathematical formulation is exactly what we will discuss now. So what I'm going to do is, I'm going to derive a few equations which are given in the textbook, but they may not be in the order. But order is not important anyway, so let us not worry about that. Let me give the heading: interference of light. Interference of light. So what kind of a diagram can we have here? Uh, of course, we have a source of light. It can be a bulb, okay, and then you have two slits, okay. This is S1, this is S2. So there are two slits, and because of these two slits, you get a pattern on the screen. This is the screen. Okay. Let the distance of the screen from the slits be D. Let the distance be D. Let me write it here, capital D. Okay. And let me draw this as a 0. Okay. This is the 0. And this line is basically the midpoint of S1 and S2. So this is the projection. This 0 is the projection of this 0. And this is the midpoint of S1 and S2. So from this 0, let me call this direction as, since we are going in up direction, let me call it Y. Okay. So at any point, let us say at this point, this is the point P, located at a distance Y from O. And I want to know whether I will get a bright band or a dark band at point P. So a ray of light from S1 will go like this, and a ray of light from S2 will go like this. Okay. And on now the next thing we ask is, on what factor, on what factor does it depend on that, whether at point P will I get a dark band or a bright band. Okay. What factor does it depend? And if you understand the initial part of the formulation, everything follows. So it is very important to understand how you begin the derivation. So we begin the derivation by understanding that the factor on which it depends that point P will experience bright band or a dark band is the path difference between S2P and S1P. So the answer is path difference. Path difference, as the name suggests, is basically the difference in the path, difference in the distance covered by the two rays. Okay, so the path difference over here is going to be S2P minus S1P, because S2P is greater, as we see in the diagram. So we have S2P minus S1P as the path difference. Okay. Now, what can we do about this? I mean, this is what we want. Okay. S2P minus S1P is how much? Okay. And this question mark, when we find, we will apply a few optics related concept to this answer, and we will arrive at the answer, whether it will be a dark band or a bright band at point P. Okay, so let us try to understand, let us try to derive what is this equal to. S2P minus S1P is equal to how much? Okay, so for that purpose, what I'm going to do is, I'm going to call this distance between the two slits as D, small letter d. Okay, d is the distance between the two slits. So this O will be d by 2. This will be d by 2. Okay, this will be d by 2 and this will be d by 2. Now, why do I need this? I need this because I see over here that I can apply Pythagoras theorem to find S2P and S1P. Okay, so this distance over here, this distance over here is y minus this much. Okay, because from here to here it is y, O to P, OP is y, and I want this distance over here. So this distance is y minus this small area, a small length, and this small length is nothing but d by 2. So this will be y minus d by 2. Okay. So applying Pythagoras theorem, apply theorem to triangle S1. Let me call this as M, and let me call this as N. Triangle S1MP. Okay. So you have S1M whole square plus MP whole square is equal to S1P whole square. The hypotenuse square is equal to sum of the legs square. So S1M, we understand it as equal to the distance between the screen and the slits. So this is nothing but d square. Plus MP. MP is y minus d by 2, as we just derived. Y minus d by 2 is equal to S1P square. So S1P has no name. We will just keep it as S1P square. Okay. Similarly, let me call this as equation 1. Similarly, if you apply Pythagoras theorem to triangle S2NP, we get d square plus y plus d by 2 square. Why d by 2 square? Because here it is more, d by 2 more is required, d by 2. So d by 2 whole square is equal to S2p whole square. Okay. Let this be called equation 2. Now, as I said, what are we interested in? We are interested in S2p minus S1p. So let us do 2 minus 1. So if I do 2 minus 1, what do I get? Gives d square plus y plus d by 2 whole square, sorry, whole square minus d square minus plus minus y minus d by 2 whole square is equal to S2p square minus S1p square. So this is what I have. Now, if I was interested in S2p square minus S1p square, then this would have been something useful for me. But I'm not interested in that. I'm interested in S2p minus S1p. So can I extract S2p minus S1p from this? The answer is yes. I can extract S2p minus S1p from this. So this is a square minus b square. So I can write a plus b into a minus b using a square minus b square as a square, sorry, undo नहीं हो रहा है. Okay, I'm going to erase. A plus b into a minus b. Okay, so I write d square cancels and I have y plus d by 2 whole square minus y minus d by 2 whole square is equal to S2p plus S1p S2p minus S1p. So this is what I have here. Okay. Now what can we do about this? We can write S2p minus S1p, sorry, S2p plus S1p as 2d, because you see we can approximate this using S2p is nothing but approximately equal to d. Okay, S2p is approximately equal to d. I mean, one may say, oh, this approximation is not good, but I will tell you it is in comparison good. In comparison to whom? In comparison to S2p minus S1p. So in comparison to this, it is a good approximation. I'm not able to undo. I don't know why. So S2p is approximately equal to D. S1p is also approximately equal to D. So I can write S2p plus S1p is equal to D plus D. Actually, approximately equal to 2D. Okay. So let me plug these values in this value over here in 3. Sorry, not in 3. not here basically, over here. So I get y plus d by 2 whole square minus y minus d by 2 whole square is equal to s2, this is 2d into s2p minus s1p. Okay. Now what we have here is this equation. If you evaluate the LHS, you will find that applying a plus b whole square formula, here you have a y square, you have minus y square, d square by 4 minus d square by 4. So things get cancelled over here, and what is left is yd plus yd, which is 2yd. Okay, 2yd d s2p minus s1p. Okay, this gives us s2p minus s1p is equal to 2yd whole divided by 2d. Therefore, s2p minus s1p is equal to yd by d. Okay, so this is what we have here. So we began by asking what is s2p minus s1p, and we arrived at saying s2p minus s1p is yd by d, where all these three terms are well defined. We know what these three terms mean. Okay, now the question that we asked in the very beginning was, will I get a bright band at P or a dark band at P? Was the question. So the next thing we apply here is the optics concept. The understanding that for constructive interference or for a bright band, in other words, constructive interference. This is another term that you should know. Constructive interference. Uh, the waves should have a path difference of n lambda, 1 lambda, 2 lambda, 3 lambda, something like that. What I mean by that will become clear. Suppose you have a wave over here, okay? Let me draw a wave. This is a wave, okay? And there is another wave which is going to interfere with the previous wave. So if these two waves interfere like this, then the resultant amplitude will be larger, even larger. Okay. So if they interfere like this, the resultant wave, will have a little bit less of the amplitude. Okay, so it depends. So if it interferes like this, then there will be destructive interference and the amplitude will be zero. This is out of phase. Okay, so you see the crest is interfering with the trough. Crest and trough cancel and you get a straight line. Crest and crest, trough and trough, they both add up and you get a larger scale, larger amplitude. Okay, so now if you have a, I mean, a wave like this, okay, and the path difference is basically the difference in the path. Say the upper wave have covered this distance lambda, and the lower wave is now interfering two waves ahead, 2 lambda ahead, but still crest is meeting the crest, trough is meeting the trough. So the path difference in this two is in the two waves is 2 lambda. Okay. If I go further ahead, the path difference is 3 lambda. So if you have 3 lambda, 2 lambda, 1 lambda, then and so on. Then you have constructive interference. Okay, so the constructive interference occurs when path difference, let us call it delta L. Path difference is lambda, 2 lambda, 3 lambda, and so on. Okay, which is nothing but n lambda, where n is equal to 1, 2, 3, and so on. So if the path difference is n lambda, you get constructive interference, that is bright band. Now, what is path difference here? Path difference is nothing but this. Okay, so that is to say delta L is equal to yd by d, where delta L is equal to S2p minus S1p is equal to path difference. Okay, so this path difference for constructive interference is n lambda, which is nothing but yd by d for bright band, which gives us y is equal to n lambda d by d. Okay, so this is the condition. This is the condition for uh, bright band. So let me write here condition for bright band. I'm sure you must be having this equation somewhere in the textbook. Let me show it where. 10.13. This is 10.13. 10.13. So this is equation number 10.13 that we just derived. Okay. Now what is the condition for dark band? For dark band, also called as destructive interference. For dark band, that is destructive interference, what is the condition? The condition is that, let me take a new page here. Yeah, we have two waves. Let this be the wave in question, and you have wave in question to interfere. Now, if the waves interfere like this, then you get a constructive interference. But if a trough meets a crest and a crest means it meets a trough like this, then there will be a destructive interference. Destructive interference again. Destructive interference again. So you see, destructive interference can take place whenever the waves are meeting like this. So this is, let me see. This is the difference is lambda by 2. Okay, and lambda by 2 plus lambda gives you 3 lambda by 2. 3 lambda by 2 plus lambda gives you 5 lambda by 2. So for destructive interference, the path difference should be 3 lambda by 2, 3 lambda by 2, 5 lambda by 2, and so on. And this can be mathematically written in two ways. One such way is this: n by 2, n minus 1 by 2, lambda by 2, where n is equal to 1, 2, 3, 4, and so on. 1, 2, 3, and so on. Okay. So this is the condition for dark band, n minus 1 by 2, lambda by 2. Okay. Delta L is equal to n minus 1 by 2, lambda by 2, which is nothing but we have proved it to be yd by d, which is y small d by d. Okay. So isolating y, I get lambda d by d like this, and 2 over here and n minus 1 by 2. Sorry, this d will be down. Okay. I'm sorry, here there will be no 2. It will be just lambda. Did I write 2 here? Here there will be no 2. Okay. So I mean, if you want to verify, you all you have to do is, for example, this number is, if I put n is equal to 2, I should get 3 by 2 lambda. For n is equal to 2, I get 2 minus 1 by 2 lambda, which is nothing but 4 minus 1 by 2 lambda, which is nothing but 3 by 2 lambda, hence verified. So this is number 2. So I put n is equal to 2, I get 3, I should get 3 lambda by 2. If I put n is equal to 3, I should get 5 lambda by 2, and so on, and I indeed get that. Okay, so that is something which is verified. So let me complete this. Yeah, so this is what we have here, uh, lambda d by, this is the equation. So let me, yeah, this is the condition for dark band, condition for dark band. So let me see which equation is this. This is equation number 10.14. Now you see here it is n plus 1 by 2, and I have written here n minus 1 by 2. But the difference between the two is that here n can be 1, 2, 3, and so on, and here n can be 0, 1, 2, 3, and so on. So here 0 is not included, 0 is not allowed. So if you want to allow 0 as well, then you can write it as n plus 1 by 2. That is why I said there are two ways of writing this. Okay, so this is correct, that is also correct, or n plus 1 by 2 lambda d by d, where n is equal to 0, 1, 2, 3, dot, dot, dot. And this is equation number 10.14. This is equation 10.14. So, to answer the question whether I will get a bright band or a dark band, all I have to do is I have to plug the value of y in 10.13 and check whether it satisfies the equation. If it does, then it will be a bright band. If it doesn't, then I have to check whether it satisfies 10.14. If it satisfies 10.14, it is a dark band. Okay. So this is what we have as the derivation for a bright band and a dark band. All right. One last thing that we will cover, and then we will stop this small video. Let me expand the canvas. Something called width. Okay, width of fringes, fringes slash bands. Okay, so how do we find the width? Okay, by the way, fringe and band are synonyms of each other. So if you are wondering what is fringe, fringe is basically a synonym for band. Okay, so let me copy this to this page over here. Okay, now what do I mean by width of the bands? Okay, the width of the band is basically, you see, this is this distance over here from bright to dark to bright. Okay, so sorry, bright to dark is the width. The distance between any two successive dark or successive bright fringes is the width. Okay, so it depends. I mean, what you want to call the width. The width we are calling, that is the textbook, is this. So bright to bright, this is width W, or dark to dark, this is also width. Both are equal. Okay, width. Width is defined as width W is defined as distance between any two successive, successive means आगे मतलब just बाद वाला, consecutive, two successive bright or dark bands. Okay, so to find W, what do we need to do? All we need to do is consider uh, any of the two conditions. Bright conditions, ये वाला condition का consider कर देते हैं. So select rectangle. This is the condition for bright band, and I plug it over here. Okay, this is the condition for bright band. Now the first bright band, I put n is equal to 1. Okay, sorry, the first bright band will be n is equal to 0. Uh, well, it depends what you have considered n over here. Here we have, by the way, a small addition over here which I need to do is this. Here you can have 0 as well. Why? Because the path difference, the minimum path difference that can have, that the two waves can have, is 0. Okay, then the next allowable path difference is lambda. Okay, so 0 is also a possibility. So if the path difference is 0, you still get a bright band. So 0 is also included. So the first bright band that you get is for n is equal to 0. N is equal to 0. Okay, so that gives me y is equal to 0. So at exactly this spot, I get bright band. Okay, this is y is equal to 0. Then the second bright band, by the way, if you are wondering, यहाँ पे textbook में plus minus क्यों दिया है? You see over here, it is plus minus 2, plus minus 2, and so on. The reason there are plus minus 2 is because if you are taking plus, you are taking this bright band. If you are taking minus, you are considering this bright band. Okay, so there are two sides, ऊपर भी है नीचे भी है. So you have this as the y-axis. So if this is plus y, you also have minus y. Okay, so that is why we have plus and minus. So second bright band, I can put n is equal to 1 or n is equal to minus 1, depending on what you want. So I put n is equal to 1 over here, and in both cases you will get the same answer. Okay, so y is equal to n की जगह पे 1 lambda d by d. Okay, so इसको I will call this as the first bright band, second bright band. Now the difference between the consecutive bright bands is nothing but y2 minus y1. W is equal to y2 minus y1. So यहाँ से लेके यहाँ तक is y2 minus y1. So y2 minus y1 is nothing but lambda d by d minus 0, which is lambda d by d. So this gives me width as lambda d by d. So this is the width of the fringes. So what do we understand here? The width of the fringes or the bands depends on the distance between the slits and the screen. It depends on the distance between the slits, small d, and it depends on the wavelength of light. Wavelength is basically the color, yellow, red, violet, whatever. Okay. So the width is given by lambda d by d. So this is what we have. And in the textbook, this equation must be somewhere written. It is not written. Apparently, it is not written anywhere. But it will be useful. Okay. I guess due to rationalization, I cannot see the equation. Okay. But I hope I have not covered something that is not there in the syllabus. Anyway, if width is not there, perhaps it is not there in the syllabus. But anyway, you have something uh, extra knowledge here. Anyway, all right. So this was it for today's class. In the next class, we will discuss a few more things related to how amplitude and intensity are related to each other. So basically, equation 10.12 and 10.11. Okay. And after that, we will discuss diffraction, and then polarization is left. That's it. Okay. And the chapter ends. So we are roughly towards the end of interference part, and then we have to do diffraction part, and the chapter ends. All right. So I hope this was helpful, and I will see you in the next class. Thank you for watching.